Hey everybody, welcome to today's lesson. Today we're going to be focusing on single replacement reactions and kind of taking a deeper dive into the single replacement reaction, why it works, when it doesn't work, and being able to kind of predict the products for those single replacement reactions. So I want to go ahead and actually start today's lesson with a video and a little bit of a story. So pre-1982, the United States Treasury used to make their pennies of primarily copper. However, it was becoming more and more expensive. And so in 1982, they decided to switch how pennies were made. And so instead of being primarily copper, they're actually made of about 97.5% zinc. And so that beautiful copper color that we see on the outside is actually just a copper coating with a solid zinc inside. And so let's go ahead and take a look here at just a quick video to kind of just dive into this lesson. So what we're looking at here is a teacher who has basically taken a penny and they have scraped the side of the penny so that the zinc was exposed. And what you can see here, and I do apologize for the poor video quality, I did not film this. What we can see is that when the penny was added to hydrochloric acid, or the HCl, that we did see some form of chemical reaction, namely we can see the bubbling happening. And so we're just going to give this a little bit of time to react and see what happens here when the teacher removes that penny from the solution. And I want to pause this here for just a moment. It was a little bit hard to see at the beginning, but you could actually see in the beginning of the video that the zinc was silver and it was exposed. Notice how now there is no zinc there. Okay, and if the teacher were to actually try to bend it, like they're doing here, notice that the inside of this penny is now hollow. And so this kind of leads us into this question of what happened here? Why did the hydrochloric acid have an impact on the zinc portion of the penny, but not the copper portion of the penny? So let me go ahead and drag this screen, my recording screen, onto my other device, and we can go ahead and go from there. So again, if you're going to follow these guided notes sheets, this will be posted for you. If you do want to go ahead and follow that, you don't have to by any means if you don't want to, but I do think it's helpful to kind of have that, particularly for some of these lessons that have examples on them. So again, right at the top of this sheet, you'll notice that there is that historic story that I just mentioned, but what I want to do now is I want to go through and I want to write out the chemical equations. And so let's take a moment here to write out both reactions, both the zinc and hydrochloric acid and the copper metal and hydrochloric acid. So zinc metal is elemental zinc, and we would represent that by just using a Zn solid. Okay, and we are going to react it with hydrochloric acid, which is going to have the chemical formula of HCl, and HCl is extremely strong acid, and so it is highly likely that this was an aqueous solution where they diluted it with a little bit of water. So we're going to just assume that that was an aqueous solution of the hydrochloric acid. Now from here, what do we observe? Well, we observed specifically that with the zinc, there was bubbling, or if you think back to that term that I just taught you in class the other day, there was effervescence, right? That bubbling or production of a gas, effervescence, okay? Copper metal, on the other hand, if I wanted to go ahead and write this reaction out, okay? Copper metal is represented by Cu solid, and we are reacting it again with hydrochloric acid, which is aqueous. And what are our observations from this? Again, what we noticed throughout that video is that the HCl didn't really seem to have an impact on that copper. And so there was no reaction or no evidence of reaction with that copper. And so when we are completing a reaction and there is no evidence of chemical reaction, we can actually go ahead and use an arrow and write NR for no reaction. okay? We don't need to predict the products if there was no product made. We are going to predict the products of that zinc reaction, but we're actually going to do that down here with just a little bit more space. So we will go through and complete that, and we can always go back and add it after. So again, let's go ahead and talk about this zinc reaction a little bit further. So again, we had zinc solid, and we're reacting that with aqueous hydrochloric acid. Now, with single replacement reactions, and I talked a little bit about this in the video of types of reactions, it's important that the very first thing we do if we're going to predict the products of these reactions is to go ahead and, sorry about that, is to go ahead and determine what is going to replace what. And in order to do that, we want to specifically go in and determine the element that's on its own, so the element that's not a part of the compound, is what type of element. And by type, I mean metal or non-metal. So what type of element is zinc? Okay, zinc is classified as a metal, and we know that metals are going to go ahead and form what type of ion? Okay, they're going to form cations or positively charged ions. And this is important because what type of ion it makes is going to distinguish which element it replaces in the reaction. So now I want to go ahead and analyze my hydrochloric acid. If zinc is a metal and it forms a cation, which of those two ions, the H or the Cl, is the zinc going to replace? Well, from what we've learned, right, we know that in a covalent compound like HCl, that this is largely dependent on the partial positives, partial negatives that are formed and their electronegativity values. Now, hydrogen has a 2.2, chlorine has a 3.2, and I believe might be 3.4. I did not look it up before this video, but either way, chlorine has a much higher electronegativity, and so chlorine is going to act as our nonmetal, and hydrogen is going to act, even though it is not technically a metal, it's going to act as a metal in the sense that it is going to form the cation. Okay, so what that tells us is it tells us that the zinc is going to replace in this compound the H, and that H is going to swap spots with the zinc. Awesome. So now we want to go ahead and predict the products of that reaction. Well, the first product that I personally like to predict when I'm doing these reactions is to go through and determine, okay, well, which element is ending up on its own? That makes it really easy, right? Zinc was on its own. Zinc is swapping spots with hydrogen. So now hydrogen is going to end up on its own. So I have hydrogen on its own, okay? The next question I want to ask myself is, does H exist in nature as solely H? Okay, so zinc exists in nature as just Zn, but this is a good time to review that H and a couple other types of atoms, okay, exist as diatomics in nature. So H will actually exist only as H2. And if you don't remember those diatomics, okay, I always like to use the mnemonic device of Hofbrinkel, but it's H2O2, F2, Br2, I2, N2, and Cl2. Okay, so H2 is our first substance that's produced. That's that bubbly gas that we see. It's actually H2 is a gas. And then what's our other compound that's created? Well, here's where we have to play into the crisscross rule, or where we have to review using ionic compounds or creating ionic compounds. So zinc, okay, forms a +2 ion when it creates its ion, and Cl, which it's bonding with, has only a -1 ion. So when those two substances create a new compound, they don't combine in a 1-to-1 ratio like HCl. So it's really important that we remember to always double check our crisscrossing, because the substance that's produced here is going to be ZnCl2, zinc chloride, and that's an ionic compound, and it's going to be an aqueous form. Okay? So now that we have our products predicted, awesome work for our single replacement reaction. Let's just go ahead and just quickly balance this reaction based on what we've already learned about balancing. Okay, so we have 1 zinc on the reactant, 1 zinc on the product, so that one's good to go. We have 1 HCl on the reactant, 2 1 H on the reactant, 2 H's on the product. So we do need to correct that. And we have 1 Cl on the reactant and 2 Cl's on the product. Now again, H is elemental, so we're going to leave that till the end, but we can correct our Cl balance by adding a 2 coefficient in front of HCl, and that actually corrects our H problem as well. So now I have 1 zinc on either side, 2 hydrogens on either side, and 2 chlorines on either side. So the big question of this lesson, and aside from just reviewing what is single replacement reactions, is why did the HCl, why did that hydrochloric acid react with the zinc, but not the copper? And so it's important here to define what is called chemical activity, okay? Which is the ease with which an element reacts with other elements. It's kind of a silly definition. It doesn't really help understanding too much. But what will help us answer this question, and what I think is the most important part of this, is actually reference table J. So reference table J, again, found in your reference tables, reference table J, tells us all about chemical activity. And I've included a diagram of what reference table J looks like here on the notes sheet. But again, you should always have your reference table handy in class. Now, in order to help us determine the rule of the reaction and whether or not there will be a reaction, I want to just go ahead and analyze the elements that we saw in the 2 reactions. Now, again, it's important to note that even though Cl was part of this reaction, the Cl didn't really do anything in this reaction, right? The Cl just happened to exist there. The reaction was primarily between the zinc and the H, and the question becomes, will zinc be able to replace H in that compound, okay? Will Cu be able to replace H in that compound? Now, let's go ahead and take a look at reference table J a little bit closer and analyze the location of where each of those are. So I want to first point out that, again, H is really, even though it's a non-metal, it's actually listed here on the metals side, okay, because it behaves as a cation. And it's listed here as H2. So here we have that H that we're curious about, okay? And we have here let's do it in pink. Here is our zinc that we're interested in, and here is the copper. Now, I want to help you guys understand table J a little bit better. So what I want to do is I'm going to go ahead and I'm going to rewrite the equations for the 2 reactions that we saw or didn't see, the zinc and the hydrochloric acid and the copper and the hydrochloric acid. And what I'm going to do is I'm going to remove the chlorine from those reactions. The reason I'm going to remove the chlorine from that reaction, is because, again, chlorine doesn't actually participate or help us determine in any way if this reaction will occur. And what did I want to say here about that? I just lost my train of thought. We call that a spectator ion. That's what I wanted to say. Spectator ion, meaning it doesn't participate, it just happens to be there. So our 2 reactions are zinc solid plus H plus becomes, and Cu solid plus Zn, or I'm sorry, not Zn, plus the H plus becomes, okay? And as we remember from the beginning, there was no reaction here. There was nothing produced, okay? For the H reaction, we produced H2 and zinc ions, which were Zn2 plus ions, okay? And again, if you're having a hard time following that, really all I did was just remove the Cl minus ion from both the HCl and the ZnCl2, and I just wrote out the ions of the metals or the cations. Okay, so now let's go ahead and take a look. Now, I want to point out that, again, in this copper reaction, there was no reaction. Using table J, where is copper's relative location compared to that of hydrogen? Okay, notice that here, copper, okay, Cu falls below H on table J, okay? And what about zinc? What is zinc's relative location compared to H? Zn falls above H on table J, okay? And so what kind of statement can we make? Well, note that up here up top are most active metals, okay? Or you can think of them as most reactive metals fall to the top, and our least active or our least reactive metals fall to the bottom. And so if I were to make a general statement about when single replacement reactions will or will not occur according to table J, okay, I would say that if the metal that is on its own is more reactive, meaning it is above the element or atom it is trying to replace, okay, then there will be a reaction. If there is, or if the atom actually falls below, like we saw with copper, then there will be no reaction. Now, I did all of this using metals because that's the example that we were given here, but you can also do the same thing over here with nonmetals. And I did want to point that out. The same is true. If my element that was on its own at the beginning was a nonmetal, and I would follow the same rules as I just did here, but using the nonmetal side, okay? Now, really quickly, I know this is a lengthy video. I do apologize. It is definitely one of the more challenging concepts from this unit, but what I want to go ahead and do is I want to do a practice problem or two with you, and those are actually located just below on this sheet. So the first problem here is bromine, or I'm sorry, the first problem, the word problem, let's go ahead and write out the reactions that we need or that we are going to be looking at. So it says here bromine, or Br2, right? Br2 is one of our diatomics, is placed in a container with sodium iodide. Sodium iodide is NaI. Write a complete chemical equation and predict the product if the reaction goes to completion. Okay, so there's lots of moving parts here. First part, let's write out our reaction. Okay, we have Br2 plus sodium iodide, NaI, becomes. Now notice, I am going to write out the complete reaction and predict the products only if the reaction goes to completion. Well, how do I determine if the reaction is going to go to completion, right? In order to determine if it's going to go to completion, I'm going to use reference table J. Now, in this example, it's important to note that the element that is on its own is bromine, and bromine is a nonmetal, which means that instead of comparing metals, we are now comparing nonmetals. So which element will bromine try to replace? Okay, it's going to try to replace the nonmetal in this reaction, the iodide. Okay, so that means that sodium in this reaction, again, is going to be considered a spectator ion. It's of no real importance. In order to predict the products, we're really comparing the reactivity of bromine and iodide. So let's go ahead and scroll back up to table J here and take a look. Okay, here's bromine, okay, and here is iodide. So again, if a reaction were to occur, the element, in this case bromine, needs to fall above the element it's trying to replace, in this case iodine, in order for the reaction to happen. So taking a look at table J, will that reaction actually happen? Yes, okay, yes it will. Bromine falls above iodide. So yes, okay, Br is above I on table J. So we do need to predict our products. So in this case, again, iodine is going to take the place of bromine, and bromine is going to take the place of iodine. So I always start with which element is on its own. Okay, in this case, again, it becomes I. And then you have to ask yourself, is I diatomic? HOFBRI. Okay, so it actually exists as I2. From there, we're going to form a compound between sodium and bromine. So we do need to re-crisscross Na plus, Br minus, criss and cross, and they combine in a 1-to-1 ratio NaBr. Okay? I think I'm going to hold on to this last example for class tomorrow. So that's it for today. Thank you guys so much for watching, and I will see you guys in class.